Okay, so quarter two, the projects have built upon quarter one. Quarter one was all about learning basics of engineering and designing parts and finding things that actually work with them. And we'll talk about a few more of those skill sets in a little bit. Quarter two is about the beginnings of assembly. And so if you look at the way it unpacks, it talks about assembly, modeling, and documentation, exploded assemblies, bills of materials, things like that. So like if you're familiar with IKEA, when you open the box, you have a paper that shows you, how these things all go together. And once, we take a look at that, you'll see that, okay, all the parts are spread apart, they're numbered. There might be some information about the length of the screws or the head of the screw. All those things make work a lot easier for your clients and users. So what we're going to do is to take a look at, how this all goes together. And let me just run through a couple of these projects so you get a handle on it. So the very first project is this three-dimensional puzzle. And the way it works with students, you would give your students the task of actually finding a client. All right, they might go visit an elementary school teacher or even a nursery school teacher or somebody who has either young children or in some cases, they're used as giveaways for companies and corporations. It's just something to keep your hands occupied. Now, this puzzle that we're looking at was designed by a young student. I had them print that one out for me because I just loved the way it worked, because there's 4 pieces and it can take you 10 minutes to put this thing together if you've never seen it. Even knowing the trick, it still takes me about 5 minutes to get it together. So it's a really kind of an interesting one, and it allows us to really do the assembly process. The relationships between the pieces, and we can control how they go together. Later on, we then can blow the pieces apart, do animations of them going back together, do parts lists, materials on those part lists, and all kinds of things that go into assemblies.
Hey, Tom, do you want to talk a little bit about clearances, or are you going to do that later?
Well, yeah, we'll do that a little later. Dick's point is about how parts go together. So if you've got like a shaft going through and a wheel has to turn on that shaft, the hole can't be the same size as the shaft. Otherwise, there's no ability to turn. It is possible to do things like that. Like if you wanted to put a bearing on a shaft and, have the inside of the bearing stuck to the shaft, we throw the bearing itself, which is going to be the outside part. We put that in an oven and warm it gently. We put the shaft in a cooler so it shrinks a little bit. We slide them together, and when the temperature evens off, which is basic thermodynamics, the 2 parts are almost frozen together, and then we've got a ball bearing that basically allows it to move. So as part of designing things, especially in quarter 3 and quarter 4, we start paying attention to not only what is a dimension, but what is a tolerance? How close can we come to that magic number and still have this component work? And that's a major thing in manufacturing. So we want to make sure that we set the stage here, so when students get to that second course and they're talking about design for manufacture, that they understand what tolerance is all about and how we display that and how we read it and that type of thing. So the second project is a 2-part.
In a book like this, you can find all about tolerances and classes of fits and things like that. when you need to know that just in time with your
Yeah,
students.
and in the second course, there's a whole project that deals with that particular concept. So in this one, we have students creating this mold, and we want them to explore molds, go online and find out what are the thousands of different kinds of molds and what are the characteristics of a mold and what makes a good mold and what doesn't. Sometimes there's single-use molds. For example, if you designed a ring and you made the mold and you poured molten metal in, you have to be able to break the mold apart, clean it out in order to get your jewelry back out of the the 3D printed mold. But in this case, we're talking about maybe perhaps melting some chocolate. They make meltable chocolate that 30 seconds in the microwave, and you can pour it in a mold and then pop it back apart. But if you don't add the right kind of draft angles and things, you have a miserable time getting it apart. So students get to explore, all kinds of things about the topic of molds, in addition to learning how, lost bodies and things like that work.
Tom, let me add something to that, okay?
Sure.
You can also go to a drugstore and get inexpensive glycerin-based soap that has a low melting point, like chocolate. And they could design, a bar of soap with the kind of graphic embedded into the mold that might have their initials or the name of their school or whatever, So it isn't just chocolate. You can also do it with soap as well.
Right. There's a lot of different opportunities, and if you cut the students loose and let their imaginations hold sway, they'll do all kinds of wonderful things. And there's also casting plastics. So if they wanted to, make, component parts for something, they build the mold and then they cast it full of plastic, and then they can pull the product back out. So when you're talking product development, there's an awful lot that goes into it. And, obviously, if we're just 3D printing, you can't do high temperature things, but you can, take these same concepts or, get a 3D printer. I guess I showed some people yesterday some things that are a little unusual in 3D printing, one of them being, metal. So we can 3D print just about any material. So the coach's card is kind of an optional project. It gives students with a little bit of extra, time, something to go interview somebody else, like a coach, who needs to carry multiple things from place to place. Or for those of us who end up teaching in more than one room and we have to cart our stuff between the rooms, it's really kind of a good way to go and design to meet a client's needs. And this gets you into wheels and axles, and it's a good introduction to some of the basic machines. And the final project in quarter 2 is this reverse engineering product. And the goal here is to take something apart, to measure and do all the working drawings and exploded assemblies and components such as those that basically go into this part. And then they take a hot melt glue gun and they glue all the parts to a paper so you can see what they are. And, so you get here's the real pile of parts that make up this product. And, here's our, working drawings of it all. If they have time, they can actually print it out. A couple of years ago, we took a bolt cutter, and we obviously had to scale it, but we made all the various parts and pieces and printed it out, and it was especially for the bolts and nuts and things like that, it was a very challenging issue to get it all together and working. So there's a lot of education in doing this particular type of project. It's very popular in engineering schools because as you take something apart, you realize that every little piece of it has been designed to somehow go into another piece and lock into place.
And you
And
notice on that picture that the parts are laid out there in the way that they exploded apart. So this is kind of like an exploded disassembly.
yeah, and it's really kind of I don't know, I'm fascinated by, how things go together and, what they look like. So I might be the wrong person to judge it, but I love to go places and take a look at, how people did these things to, get them all to work. If I take a look at like a drill press from 120 or 140 years ago, I'm just fascinated. Dick had a picture of a steam engine that ran on a leather belt to power a factory, and I've been in old time factories that were run by water wheels, and they had the leather belts across the ceiling, and power was transferred, and you have to, think about, we've only been designing and drawing things out, on paper, with strict rules for 120 years maybe. If you go back the first time there's any evidence of interchangeable parts was about 200 years ago. Before that, it was like, all right, so I made this thing, and if you break a part, you have to wait while I make you a new part. You can't just pick another one out. And so there was a gentleman by the name of Eli Whitney, and most people say, oh, cotton gin. But his main contribution was really this concept of interchangeable parts. So he, during the War of 1812, he took a contract with the government to make muskets. At the end of the war, the government called him up and said, hey, where are these muskets you were supposed to make for us? And so he brought in several bushel baskets. And in each bushel basket was a different component part. And he just started picking parts at random out of these baskets, and he managed to put together a working rifle. And then, people started getting excited because it's like, oh, well, if I break a part, I could just take this other part, slop it in, and it works really well. And so that really started everybody thinking. And if you go back to Henry Ford's factories, as you walked into the factory, they would have part drawings on chalkboards, so it's like, okay, here's today's part, and they would all, sketch it out on a chalkboard. So, this concept of doing design so they all fit together is relatively new in the grand scheme of the human race. And what we're working on now is the next generation of that. So, we're abandoning things that worked well for the off chance that what we design will be that much better. So that's part of it. So that's quarter two.